For the infinite mathematical series that is shown in this example, that involves the summation of terms 1 over 2 squared minus 1, 1 over 3 squared minus 1, 1 over 4 squared minus 1, and up to infinity, we want to see whether it converges. And if it does, is there a quick way to solve this infinite series? And as a third question, is there a closed form formula, or can we find a closed form formula for the finite version of this sum that goes up to the nth term that is in the form of 1 over n squared minus 1? So that would be the third question. In this example, I want to show you that there is a quick way to solve this series and find a closed form formula for that. For that purpose, just focus on the terms of the summation. For example, we have a2, so index 2 refers to 2 to the power 2 in denominator, and we have a3, a4, and so on and so forth. And let's go up to the nth term as let's say dealing with the finite version of this summation. So 1 over n squared minus 1, that would be the nth term of this summation, so that's index n. Okay, I'm going to write these terms here. So I have a2, so let me just remove these guys. I'm going to just say a2 is 1 over 2 squared minus 1, and obviously I can write this 1 over 2 minus 1 times 2 plus 1, which is 0.5 times 1 over 2 minus 1 minus 1 over 2 plus 1. So let's keep this, and if you want to further expand this, it becomes 0.5, 1 minus 1 over 3. So let's keep this. A3 is 1 over 3 squared minus 1, which is again 1 over 3 minus 1, 1 over 3 plus 1, which can be written as 0.5, 1 over 3 minus 1 plus minus 1 over 3 plus 1, which can be written again as 1 over 2 minus 1 over 4. Alright, I'm going to do a few more terms very quickly because I need them. So 4 minus 1 is 4 squared minus 1 with the same logic and reasoning can be written in the form of, I'm going to quickly just write it here, 0.5, and we have 1 over 3 minus 1 over 5. Alright, so let me jump to, so I'm going to just extrapolate and jump to the terms that are an minus 2 and an minus 1 and an finally at the very end. Alright, so what are these terms? These terms are, again, I need them. That's why I'm writing seemingly a lot of terms here, but I need them. So this one is 1 over n minus 2 squared minus 1 equal to 1 over n minus 2 minus 1, which is n minus 3, and n minus 2 plus 1, which is n minus 1. So if you write it, you will end up with 0.5. I'm going to just write it here. So 0.5, 1 over n minus 3 minus 1 over n minus 1. For the next term, a index n minus 1, we're going to get 1 over n minus 1 squared minus 1, which is 1 over n minus 2 and n. So obviously this becomes 0.5, 1 over n minus 2 and minus 1 over n. And finally, for the term that is a index n, we get 1 over n minus n squared minus 1, so n squared minus 1, which is equal to 1 over n minus 1 times n plus 1, which is equal to, so the last term here, 0.5, 1 over n minus 1 and plus, so plus 1 over n plus 1, minus 1 over plus n plus 1. So what is the benefit of writing it this way? The benefit is, now you can see that actually we end up with a telescoping series. So this is now converging to a telescoping series in which terms are cancelling, subsequent terms are cancelling out each other. Take a look at what's going on. So for instance, this term here, 1 over n minus 1, is cancelled with a term from with minus 1 over n minus 1 from a term that is for n, coming from an minus 2. So two terms before that, And you can see this is happening subsequently for previous term. For example, it can be seen that, so I'm going to just write it here. I'm going to just highlight that this is canceling this guy. This one is cancelled out. So again, here we have dot, 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 and same thing here. Okay, so these guys are cancelling, and for instance, we can see that 1 over 3 is cancelling this one, and 1 over, let's say, 4 is cancelled out with another term here. So the only thing that is effectively remaining in this telescoping series with cancelling terms from subsequent terms would be 1 and 1 over 2, of course, not forgetting about 0.5 here, and then negative 1 over n and 1 over n minus n plus 1, and of course the 0.5 terms behind them. So when we add all these terms together as planned in the series, that we are adding all these terms together, then we just end up with, so the outcome of just summing all these terms, starting from, let's say, so k from 2 to n, ak, which is basically the summation that is mentioned here in a finite format, we end up with just 0.5, so the 0.5 that we have for all of them, and then we have 1 plus 1 over 2 minus 1 over n, so these guys now, minus 1 over n plus 1. So I'm going to keep this because this is very simple and useful, but if you want a further simplification of this closed form format, we can do so. So I'm going to just, let me just do it this way, equal to. So if you want to further simplify this, of course, we can say 0.5, 3 over 2 minus 1 over n minus 1 over plus 1, and finally, if we just further simplify this, the closed form formula becomes if you just multiply and simplify the whole thing, it becomes 3n plus 2 times n minus 1, and divide by 4n times n plus 1. So that is the closed form formula for this finite version of this summation up to the summing up to the nth term, an. Obviously, when we want to find the infinite version, as the original question is asking, we can just do the limit of this summation. So limit of, so for the infinite version, we would say limit of this sum when n goes to infinity, which obviously when n goes to infinity, if you take a limit out of this, because both numerator and denominator are polynomials of the second order, so 3 over 4 remains. Another way to look at it is when n goes to infinity, these two components approaches 0. What remains is 3 over 2 multiplied by 0.5, which is again 3 over 4. So the answer is 3 over 4, or 0.75. So that is the infinite version. I'm going to just write it here. So this one is the infinite series. So yes, the answer is the infinite series converges, and it converges to 0.75. The finite version is what is the sum that we found here. So finite version of this summation up to the nth term. So what we did is, by modifying the terms and writing them in a different way, we managed to benefit from the telescoping series properties, and we benefited from the consecutive terms cancelling out each other, and therefore we got to the final result. So this is the quick algebraic method. For the mathematical induction, I'm going to just quickly start with this. So as I showed you before here, for the finite version, we have this formula that I have just repeated that here. I have rewritten it here. So it's as if using mathematical induction, we want to say that for any positive integer n greater or equal to, so let's say p of n, which means a predicate or a statement, logical statement that says for any n belong to set of positive integer and n greater than or equal to, we want to say p of n is true, which p of n is this statement. So p of n is a predicate or logical statement that states that this sum, left hand side and right hand side, are equal to each other. So in this case, here is our left hand side, and this side is our right hand side, and we want to say that these two are equal. So I'm gonna write it here. Again, similar to any mathematical induction approach, we have to start with basis step. In this case, basis step, as you can see, the problem says start with n greater than or equal to. So our basis point for mathematical induction is n equal to 2. That's the starting point. Minimum value of n we can apply. So the basis step says examine p, the logical statement, the predicate, with using n equal to 2, the starting point. So we would say check p of n equal to 2 and see if that is correct or not. So what is p of n equal to 2? The only term on the left hand side here is the first term, because we are stopping at n equal to 2. So this is the only thing that is remaining there. So we have 1 over 2 square, I'm going to write it here, 1 over 2 square minus 1, that's the left hand side, and on the right hand side we need to substitute here n equal to 2. So we're going to get 3 times 2 plus 2 times 2 minus 1 divided by 4 times 2 times 3. And it's obvious that on this side we have 1 over 3, and on this side we have, as you can see, so I'm gonna write it. So left hand side is 1 over 3, and right hand side is numerator, we got 8, denominator we get 24. So yes, there is a match. So therefore, as a conclusion, we are saying basis step is correct. So this is logically correct. That is true. For the inductive step, so the next step in the mathematical induction is inductive step or induction step. So in the inductive step, we are going to assume that the stated predicate, which is this theory, is going to be true for n equal to k. So we say pick n equal to k, where k is greater than or equal to 2, and assume that p of k, and assume p of k is true, is true. So that would be our inductive hypothesis or assumption. Then prove that p of k plus 1 is also true or correct. So that's what we need to do. This one is going to be quick if we resort back to what we had here. So I'm gonna use the outcome we got. Which outcome? The one that I'm showing here, this one, before further simplification. So point which as we said, if we just simplify this, you get to the formula. But I'm gonna stay with the one that is highlighted in green, 0.5 times 3 over 2. So let me write it here. P of k, or inductive hypothesis, is the statement that says sum of all these terms. So let me start with what I need to prove. P of k plus 1 is what I need to prove, which says 1 over 2 squared minus 1 plus 1 over, so it is saying 1 over 2 squared minus 1 plus 1 over 3 squared minus 1 plus 1 over 4 squared minus 1 plus dot 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 plus 1 over k squared minus 1 plus 1 over k plus 1 squared minus 1, because I'm going p of k plus 1, is equal to question what? Okay, so I'm going to use the inductive hypothesis, this one, which says this portion is already the left-hand side of the p of k. So this is the left-hand side of p of k. And therefore, I'm going to, since I know p of k is true, I'm going to just, instead of writing this left-hand side, so left-hand side of induct of p of k, which is our inductive hypothesis. So I'm going to substitute that using with the right-hand side of inductive hypothesis, which is in the green formula, the one that is highlighted in green box here. So 0.5 times 3 over 2. So I'm going to do that. 0.5 times 3 over 2 minus 1 over k, up, because we go up to k. And here we were going up to n, so we had 1 over n and 1 over n plus 1. So we are now going up to k, so it becomes minus 1 over k minus 1 over k plus 1. Okay, what about the only term that is new one, the new term here that we have? Okay, so for that one, let me use a different color. I'm going to go with the black color here for this one, for this term, which is the new term, the additional term. I am going to write 0.5 1 over k plus 1 minus 1, which is 1 over k. So let me just write 1 over k. And we have minus 1 over k plus 1, which becomes k plus 2. Alright, so if we can see that there is 0.5 for both of them, and just as a recall, this one is the right, so this one is the right hand side of p of k. So this one here is the right hand side of p of k, which I substituted for the left hand side. So instead of this left hand side, I just wrote the right hand side. So factoring out 0.5, you can see that then the 1 over k and negative 1 over k cancel out each other. So what remains is 0.5, 3 over 2 minus 1 over k plus 1 minus 1 over k plus 2, which is exactly the target right hand side of pk plus 1. So this is target desired. So desired right hand side of p of k plus 1. And we are done. Because what I did was I used the information or the hypothesis that p of k is true, so left hand side, right hand side of p of k from here true, and then I showed that then for p of k plus 1, from its left hand side I can get to the desired right hand side as the formula says. So therefore we managed to prove the inductive hypothesis as well, and as a result, because the both steps, basis and inductive steps, are proven, then based on mathematical induction we can say for all n as positive integers n greater or equal to 2, then p of n is true. Therefore this whole statement based on using mathematical induction is true as well. Hence we managed to prove the closed form formula for the finite version of summation, which is what we needed. I hope that this example is helpful in terms of showing how we can quickly solve a given finite and infinite series like the one shown here, and also showing how telescoping series can be potentially used at least in some of the examples. Thanks for watching.